We present similarity in chapter 8, section 8.5, and we will see how two representation matrices of a same linear operator, obviously relative to two different bases, how do we come to see that they are similar. So it's going to be quite easy and straightforward. So let's see how it works. First thing is to notice that we are working with a linear operation from V to V. So V is finite dimensional linear space. In our case, it's going to be Rn. So we have the same linear space as domain and codomain. So it's same input and output space. They are finite dimensional, so let's say Rn and Rn. So we are given that as a configuration of the problem, and then we have two different bases. Obviously, every non-empty finite dimensional linear space has infinitely many bases. In this case, we are just taking two of them, B and C, and see what will happen with their representation matrices. So we have a linear transformation T, and then we will have a representation matrix of a linear transformation T relative to basis B, B, right? Because it's T goes from V to V, so the same linear space. So the basis here we are choosing B in this case, so it's the same basis for the input and output, obviously, because it's the same space. So we have this representation matrix relative to the basis B, and then we have another representation matrix of the same linear transformation, but this time relative to the basis C, so a different basis for the same linear space. So what's the relationship between the representation matrices of the same linear operator relative to two different bases? Remember, when we have the same domain and codomain, then the linear transformation, we have a special name, and we call it linear operator, just to make sure that we know that the input space and output space are the same. So what happens to two matrices, two representation matrices of the same linear transformation, but these two representation matrices are relative to different bases? Well, they are linked, and the link is this matrix P, which is invertible, and this is the matrix that is actually change of basis transition matrix from the basis C to basis B. So this matrix obviously is square always, and it is invertible always, and its inverse is on the other side. So if we remember the definition of similarity of two matrices, if we consider TCC as a matrix and BCC as a matrix, then this actually fits the definition of two similar matrices. All we needed is a matrix P that is invertible, and it goes on both sides, like P and inverse of P. So that's why we say that representation matrices of a linear operator, so both of them are square obviously, are similar because they satisfy the definition of similarity. So that's the main result for this section, and the only work is to apply it to see how it works. What is important is to understand that the matrix P is change of basis transition matrix from basis C to basis B. So we are going to see how to get this relation here, let's say naively and intuitively. Another interesting thing is that the determinant of the linear operator, so T from V to V, is equal to the determinant of the representation matrix in any basis. So if you take representation matrix in basis B, well, you compute that's a matrix, obviously square matrix, and you compute the determinant, that's the determinant of the linear operator here. Obviously the eigenvalues too. We will say the same thing. So if I change a basis, obviously I'm going to get a different representation matrix. But the good news is that the determinant is the same, and we see why. Because the determinant of this side is product of determinants on the right side. But determinant of this matrix and this matrix, since they are inverse of each other, so if I have determinant A here, this is 1 over A, so they cancel. You see it's an invertible matrix. So that's why determinant of TCC is the same as determinant of TBB. Simple. So that's an interesting property. So determinant of a linear operator, so from V to V, is equal to the determinant of a representation matrix in any chosen basis. Obviously, when we go from V to W, then we don't have square matrices. So we cannot talk about the determinant. So this is really related to linear operators because we go from V to V and we use the same basis. Okay. So those are the main results. There's not big deal here. It's simply this result, and we will see how to find it. Important reminder again is that linear transformation, or in our case operator, because we go from Rn to Rn. Linear operator works on objects, in our case vectors from Rn. And the result of the action of T are objects, in our case again vectors in Rn. So that's why we say linear transformation works on objects. Representation matrices, they work on coordinates of objects. And representation matrix depends on the basis we choose. Okay, so if we choose a basis B for Rn, then the representation matrix is given here BB, right? So that's obvious thing. A reminder again, if I take a basis B here for Rn, the representation matrix TBB, we remember how we build it. We take each of these basis vectors, we apply T to each of them, so T of B1, T of B2, T of Bn, and then we need to find the coordinates of those vectors, so the coordinates of TB1 in basis B, and then we put that result in the first column. And then for the second column, we need to find the coordinates of TB2 in basis B. So there's work to do before we build this. Obviously, if we change a basis, if we have a basis C for Rn, so the same linear space but different basis, the representation matrix TCC, so it takes as input the coordinates in C, so I need to compute T of C1 and then get the coordinates of T of C1 in basis C and then put the result in the first column. For the second column, I compute T of C2, so that's a vector, and then I need to find the coordinates of that vector in basis C. So there is a work to do, and then the result I put it in the second column. So that's how we build these representation matrices relative to the basis, different bases. Okay, so this is just a reminder. It's important to have that in mind. Obviously, we said that the representation matrix works on coordinates. So when I have TBB, it multiplies the coordinates of the vector V in basis B. And then once I'm done with the computation, what I get as a result are the coordinates in basis B of the image of V under action of T. So coordinates of B in B of TV. Okay? So that's very simple. That's what it says. Multiply the coordinates of V in basis B. Once you're done, what you're gonna get are the coordinates in basis B of TV. Okay. If I have a representation matrix TCC, in this case, I need to find first coordinates of V in basis C, then do the product, and as a result, I'm gonna get the coordinates in basis C of TV. So what I'm getting here are the coordinates of the image. In this case in basis B, in the previous case it was in basis B in the previous case, and here in basis C. So those are just reminders to have fresh in mind and be ready to understand the process, how to get the big formula for this section. So let's see how that works actually. So I'm given some linear transformation. In this case, it goes from Rn to Rn, so we call it linear operator. And I'm given some vector v in Rn, and we have two different bases, B and C for Rn. And I'm given the representation matrix BB. So representation matrix of a linear transformation T relative to the basis B. My job is to find the representation matrix TCC. So representation matrix of the linear transformation relative to the basis C. How do I do that? So that's what we need to see. Remember, representation matrix TBB takes as input coordinates of a vector in the basis B. Once we are done doing the multiplication matrix vector, what we are getting as output are the coordinates of TV in the basis B. Again, right? BB. For the representation matrix TCC, this one requires inputs to be coordinates of the vector V in the basis C. And then once I do the product, I'm going to get as output the coordinates of TV in the basis C. So those are the reminders that will be useful to build this big and beautiful equation that we saw at the beginning. So let's see how that works. So let's see how we get the big result. What we have are the bases B and C of Rn, and eventually we have some vector from Rn, and we are also given the representation matrix relative to basis B, so T of BB. So that's what we have. Now what we need to get is the representation matrix for the same linear transformation relative to basis C, so T of BCC of CC. Okay, so we have TBB given, but we know that TCC needs to work on the coordinates in basis C of a vector. Okay, but we only have this guy. So what do we do? Well, we need to use this representation matrix. That's the only thing we have. And eventually we will have this guy here, the coordinates in basis C. So that's a problem because this representation matrix needs coordinates in basis B. And then it does the job and it gives the coordinates in basis B as a result. So having an input in basis C, it's a little problem, but we need to deal with it because TCC will work with these people. So what do we do? Well, not a big deal, because we can always use the change of basis transition matrix from basis C to basis B. Because this representation matrix relative to the basis B needs coordinates of V in basis B. But we have it in basis C, so what do? Not big deal, we take those coordinates, multiply by the transition matrix. So change of basis from coordinates in C into coordinates in B. So we know how to build this. We remember how to do that. So we need to solve a system like this by Gauss-Jordan, and then the solution is given here. So that's how we build the transition matrix. We put the bases there and then do the work, and then we get our change of basis transition matrix. So we are going to use this guy, this transition matrix, multiply by the coordinates of vector V in basis C, and then what we get are the coordinates of vector in basis B. Yay! So now we can use this to multiply with the representation matrix relative to basis B. So that's a trick. We use the transition matrix, change of basis from basis C to basis B. Okay, so we also know that the image of V under action of T in coordinates of B is given by this product, obviously. Representation matrix times the coordinates of the vector in basis B. But we know that these coordinates, ta-da, they're given here. So T of V in basis B, I replace this guy by this expression here. Just plug and play. Okay, so that's it. So now I have the coordinates in basis C as input, then I convert them by this transition matrix into coordinates in basis B, and then I multiply them by the representation matrix, and what I get as a result of all this are the coordinates in basis B of the image of V under action of T. Okay, so now, so that's the easy part. What we need to realize, these are coordinates in basis B. Good. What we want at the end of the day are the coordinates in basis C. But that's not a big problem. We just need to convert the coordinates from basis B into coordinates in basis C. How do we do that? Well, guess what? We use the change of basis transition matrix. So now we have the coordinates in basis B, we need to convert them into coordinates in basis C. We are going to use the change of basis transition matrix from basis B to basis C. Well, we remember, hey, this guy is just the inverse of the previous guy. The transition matrices are square and invertible, we know that. So to go from one basis to another, once you have one matrix, well, its inverse gives you the transition from B to C. Okay, cool. So that's easy. Well, it's easy. You need still to compute it. So once we have that, this means that now the coordinates in basis C of the result are just our coordinates in basis B times the transition matrix, the change of basis matrix. So this will convert the coordinates from basis B into coordinates of basis C. Yes. So all I do now is just plug and play. So this guy still stay the same. This guy copy paste. This guy, I already have its expression. It was the representation matrix times change of basis from C to B times coordinates in basis C of the vector. Cool. So now job is complete. So I have the coordinates in basis C of the image, which is equal to all this. We remember that the coordinates in basis C, what does it mean? It means I'm multiplying the representation matrix CC by the coordinates in basis C of the vector. That's the definition. Okay, so that means that this part is equal to this part. Well, obviously, same input, and that means that TCC is actually all this part here. I just recognize them and I write it down. So T, representation matrix relative to basis C, and representation matrix relative to basis B, they are linked. And the link is the change of basis transition matrix from basis C to basis B, and this guy is obviously the inverse of the previous. We know that. So that's why this actually looks like the definition of similarity of matrices, this one, C and B, right? So that's how we got the big result. It's quite intuitive actually. You just need to think of how are we going to use these representation matrices, and then you go step by step and you convert using the change of basis transition matrix. You convert coordinates from C to B, then multiply here. The result is going to be in coordinates in B. Then you need to convert those coordinates into coordinates of C, and then that's it. So that's the natural progression. So that's how we got the big result. So these two matrices, representation matrices B and C, they are similar by the definition of similarity. Also, they have the same determinant, obviously, because this and this, they are inverse of each other. So determinant of this is 1 over determinant of this, so they simplify. So determinant of this matrix is equal to determinant of this matrix here. So that's kind of straightforward. here is an example. How do we apply all this? Let's see how it works. It's a little bit long, but it's not complicated at all. It's simple. So we have some linear transformation from R3 to R3. So it's called linear operator because the input space and the output space is the same. And we are given a basis B of R3 with these three vectors that are linearly independent. And also we are given the image of each basis vector under the action of linear operator T. So we don't know what is this linear transformation of this linear operator. We don't know what it is, but we know that its action on each of the vectors of the basis B is given here. So that's all we know. So what we need first is to find TBB. That's our job. So and we need to find the representation matrix for the linear transformation T relative to the basis B. So basis B for inputs and outputs, obviously. Now we remember how this is built. We need to find coordinates of each of these images in basis B. So to build the representation matrix, to build the columns, we need to find the coordinates of each image in basis B. That's the job. That's the first part. So those will be the columns of our representation matrix here. So it's going to be square matrix, obviously. So what we need to do is to solve so the basis B, the three vectors, and then each of the images that is there. So we put the basis vectors in order, and then each of the images also. And now we solve and we find, as a result, the coordinates of each image in basis B. So once it's done, so this takes some time, obviously, you solve by Gauss-Jordan, we get these coordinates here of each image in basis B. So now the last step, we put each of them in corresponding column, and we are happy. So first one in the first column, second one in the second column, third one in the third column. So now we have the representation matrix of linear transformation T relative to the basis B. Okay? So B for input, B for output, this is linear operator. So we still don't know what is the linear transformation, and we don't need to. But we know what is the representation matrix relative to the basis B. Okay, cool. Job done. So now, let's make things complicated. Let's find the representation matrix relative to some other basis C for the same linear operator. Let's see how that works. Obviously, we are going to use the formula we just learned. So here we go. We will use the representation matrix relative to basis B for our linear operator in order to get the representation matrix relative to the basis C. And basis C is given here with three vectors W1, W2, W3. They are linearly independent, obviously. This is another basis for R3. So what do? Well, we use the equation we just learned, which is quite intuitive. We have the representation matrix, BB. This needs to eat the coordinates in basis B and gives out the coordinates of the image in basis B. So for this matrix to work, we need to convert the coordinates from basis C into basis B using the change of basis transition matrix from basis C to basis B. That's what we saw already. So we'll multiply by coordinates in C. This will convert them in coordinates in B. We do the job. So this one here does the job of the linear transformation, gives results in coordinates in B, and we convert those coordinates using the change of basis transition matrix from basis B to basis C. That's the job. That's how it works. Obviously, these two guys, these change of basis transition matrices, they are inverse of each other. Huh? We know that. You don't need to show that, we know it. They are inverse of each other. Okay, so we are almost there. We need to compute this guy, and then we need to compute its inverse, which is this guy. And then we multiply everything, and everybody's happy. So how do we find the change of basis transition matrix from basis C to basis B? Well, we know how to do that. We need to solve a linear system B slash C. So we put the basis vectors from basis B here slash basis vectors from basis C. So these guys are from basis C. Put them there, solve using Gauss-Jordan, and 2 days later when we are done, we get this change of basis transition matrix from basis C to basis B. Yes sir, we are happy now. So we got this guy done. We have this guy done, now we need this guy. But this guy is inverse of him. Okay? Another way of doing it is swap these two guys and solve again. It's up to you what you do, it doesn't matter. You can find the inverse of this or go back and solve C slash B. So a different one. So we need our inverse. So transition, change of basis transition matrix from basis B to basis C. Either we compute the inverse or what we already got, transition matrix from basis C to basis B. So that's what is done here. Compute the inverse, it takes 2 days. Or you can solve C slash B. It's up to you. Whichever way you choose, you're going to get the same result. And in both cases, you need to work a little bit. It's not free, so this takes time. And then we get the transition matrix to change of basis from B to C. So finally, we use our formula, the representation matrix relative to basis C for our linear operator T is given by this formula. Now we have all the pieces, we just plug them into the expression. So we copy this matrix here, we copy TBB, we copy B, the change of basis transition matrix from C to B, and then we do the product, 2 matrices at a time. It's going to take a while, and once you do all the calculation, hopefully without errors, you'll get this matrix here that is actually the representation matrix relative to the basis C of our linear operator T. So that's how we work with it. It's a lot of computation, but they are fairly elementary computations. It just takes time to do them. Let's push the fun to the ultimate level. Let's find the standard matrix. So we are going to use the representation matrix relative to basis B, so TBB, for our linear operator T, and we want to find the standard matrix, representation matrix relative to the standard basis of R3. Obviously, we will use the equation we found earlier, and this is the change of basis transition matrix from basis S, so the standard basis, to basis B. And obviously the other guy is the inverse of it. So standard basis, we remember, is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so how do we find this transition matrix from standard basis to basis B? Well, it's simple. We need to solve the system. So solve by Gauss-Jordan. Obviously the standard basis on this side is identity. So basically we are looking for the inverse of the matrix on the other side. So once we are done with the Gauss-Jordan, we get this matrix here, which is the change of basis transition matrix from basis S, standard basis, to basis B. Its inverse is obviously the change of basis transition matrix from basis B to basis S, the standard basis. So the inverse of this is obviously the matrix on the other side, because this is how we compute the inverse of a matrix. Like, you put the matrix and then slash identity. So once we get this, the inverse of this is the original matrix. Or if you don't believe, you just do the job here, right? You'll have identity B, so this is already solved, you get B, all right? So that's easy. So once we have these pieces, so we have the transition from standard to B, and then we have its inverse already, it's easy in this case. Then we can plug everything back into the equation. So here it is, we are plugging everything back, putting all the pieces together. So the standard matrix will be, so all these 3 matrices multiplied, so we multiply 2 at a time, so it's going to take some time, obviously. So once you're done, you get, if no errors, something like this, the standard matrix. So this is a standard matrix or representation matrix relative to the standard basis, as you like. Okay, so that's it. But now once we have this, we can actually discover what was the linear transformation or what was the linear operator actually from the beginning. We didn't know what it was. But now, since we have the standard matrix, it's going to be easy to find out. We just need to multiply the standard matrix by the standard coordinates of a vector. So in a basis S, so in the standard basis, we know that this is equal to the components of the vector, obviously. So just do the product. This is like generic vector from R3. So X is some generic vector from R3. And we do the product and we get this. So obviously, so T of X, our linear operator, so which works on the vector, let's say, just write it down, x1, x2, x3, explicitly. So this is our linear operator actually. It was a mystery during all this time, but now we discovered what was the linear operator. So we see that we can have obviously several representation matrices for our linear operator or any linear transformation. And this is the way we use the formula. And also we remember that the determinant for the operator is the determinant of the representation matrix in any basis. So determinant of this matrix or determinant of the representation matrix relative to basis B or determinant of representation matrix relative to basis C are equal, all equal. It's beautiful. So this part of the material is super easy, straightforward. It requires some heavy computation though. It's all simple, but you still need to compute. So there's no way around it. You see, you need to compute one matrix, then you need to another one, and then the inverse of this one. So it's going to require some time. The important thing is to know what to do, how to do it, and then doing it just requires the time to do it. Nothing complicated at all. Everything is straightforward and easy. Couple of practice problems should help. So to practice, you have some problems in the book, or you can invent your own problems. It's not complicated at all. So these problems you have in white cover book and yellow cover book. I suggest you do both sets. Some of the problems are identical, some are not. So you see here you have more problems. So try to solve as many as you can just to make sure you understand the process, you know how to do it. And obviously it's going to take some time for the computations, but as long as you know what needs to be done, it's going to be just fine. Obviously practice is needed, process is needed, so those are the difficult parts here because you really need to compute heavily.